Here is an artist's conception of the idea of quantum foam. The notion is that energy fluctuations within space may be enough to change the shape of space and time, to cause them to wiggle and stretch into higher dimensions. We're accustomed in general relativity to making two-dimensional analogies where we draw space like a rubber sheet and then imagine putting a mass in that sheet and having it gently bend that two-dimensional sheet into a third dimension. And then to say that our space is three-dimensional and mass would bend it into a fourth. Quantum foam is the idea that just quantum fluctuations, something that is built into the nature of space itself, would be causing this to happen if the energy is great or the size scale small. Quantum foam is a purely speculative idea, but it's an extrapolation of physics we know into a realm that we're just simply not able to measure. We can't measure things as small as the scale where we believe we'd be able to notice the effects of quantum foam. So while on the tiniest of size scales, all of space around us may be full of quantum foam, we haven't been able to test that. The other circumstance where quantum foam leaps to its power should be where energy is concentrated to enormous densities, as was true at the very beginning of the universe, shortly after its creation, in the very first split second of the Big Bang. If we extrapolate our ideas about quantum physics and our ideas about general relativity, which says energy in any form should distort the shape of space, then we run into the idea of quantum foam right near the very first instant of the history of the universe. The age of the universe, at the time when quantum foam was basically just tearing all space asunder, is remarkably simple to calculate. It's a formula that involves three fundamental constants of physics. You will recognize two of them immediately. Big G there is Newton's gravitational constant. C, the speed of light. H in this formula is called Planck's constant, a fundamental constant of quantum mechanics that tells us the energy scales where quantum physics randomness begins to come in. The formula is not one I expect you to memorize, but the time that comes out is just a little bit more than 10 to the minus 43 of a second. It means that 10 to the minus 43 of a second after creation, it was all quantum foam. And before then, we haven't a clue. We really don't know, and nor should we dare to claim to know. That time of 1.35 times 10 to the minus 43 of a second has a special name. It's called the Planck time. That was the time when the energy density, the concentration of energy in the early universe was so great that it was bending space-time, and yet the quantum physics that was active when everything was so concentrated was causing all the random fluctuations of that energy in the strength to create the quantum foam. At an earlier time, we would expect the energy concentration to have been even greater. And one big question mark is how it would be possible for space or time to even exist under those circumstances. Again, we really cannot claim to know anything about what might have happened before the Planck time, because when we extrapolate physics as we know it to anything before, things begin to get completely absurd. We may never know what happened before the Planck time, but to understand the Planck time requires understanding general relativity and quantum mechanics both together in more detail than we know them now. So let's just keep in mind that the very idea of quantum foam has never been experimentally confirmed and may simply be a speculation, with reality at the Planck time being, in truth, something else. But we can advance the movie forward a little. The universe from that time was expanding and cooling, expanding and cooling, expanding and cooling. And soon these fluctuations became smaller and smaller and smaller. And we were into a more familiar kind of physics of fundamental particles interacting with one another and exchanging energy. Then maybe about 10 or 100 million times further in the future, not 10 to the minus 43 of a second, but perhaps 10 to the minus 35 or 10 to the minus 34 of a second, something else interesting happened. To understand how the universe was changing and what effect that was having on things, let's take a look at the strengths of the four fundamental forces that we know of in nature. There is gravity, the weak nuclear force, electromagnetism, and the strong nuclear force. And they are ordered over on the left side of the figure you're currently viewing in order of strength. At very, very low energies, low temperatures, basically what the universe is like today, the strong force is overwhelmingly the most powerful force in nature. Electromagnetism is the second most powerful force. The weak nuclear force is weaker than that. And relative to the others, gravity is incredibly feeble. I'll remind you that a mere refrigerator magnet has enough power, enough force attached to the refrigerator to withstand the gravitational pull of an entire planet trying to pull it down. In that sense, gravity is profoundly weak. As we increase the energy, interesting things happen. The strong force we have observed becomes weaker when energies are higher. And the weak force becomes stronger. And at energies that we have been able to create in particle accelerators, there comes a point where the electromagnetic and the weak forces combine not only to exactly equal strength, but even alter their properties and behaviors such that they act as a single force. We call that the electroweak force. And the electroweak force also, as energy is further increased, gets stronger. Gravity will always get stronger as energy is increased. Gravity is a distortion of space-time due to the presence of concentrated energy. The more concentrated the energy, the stronger the gravity. At energies that are far beyond anything we've been able to create in a particle accelerator, we expect, from extrapolating the trends, that the strong force and the electroweak force would also join together in a grand unified theory force called the gut. And that at even higher energies, the energies that would have been around at the Planck time, we would have even gravity joining with the gut force, so that at the Planck time there was only one force in nature, one superforce. And we have to unify general relativity and quantum mechanics in one single theory. The theory of everything. Physics does not yet really have a theory of everything. That would have to include all four forces of nature. But we're working on it. We're on the blackboard. And we like to give it a cute name.